Hello everyone, Adlash here. Today we're going to be trying to figure out how to develop AI for video games. And this is a big complex topic, and I'm going to be trying to tear it down piece by piece, video by video over a long series of time. So this is like the first one that I'll probably be making. And you can see over here that we have some like little agents, I'll just call them agents, enemies, same idea. And they're able to find and follow me by going around obstacles. There's no pathfinding here, there's no navigation mesh, there's no navigation mesh. There is a tile map, but that's used for the walls. There's no complex math involved. It's more based on heuristics and intuition, which we're going to try programming in. And it does lead to sometimes dumb AI over here, as you can see. As you can see, it's trying to get to the closest path, but it's also possible that it can go around, as you saw previously, like 3 seconds ago. It went around this bend and it was able to come find me. So it's kind of like programming a human almost ish in a way. That's enough rambling. God, I ramble so much. Okay, we're going to be using Godot version 3.4, and let's get right into it. So let's start by describing the screen. Let's start by describing the scene. As you can see over here, we have the world. We have a player, which is just a regular kinematic body 2D. We have the world again, but this time it's just the tile map of the actual. It's a tile map, and this tile map has collision setup so that the player and the enemies or agents can like walk around it. As you can see, there's no navigation mesh that we're using because sometimes navigation meshes are hard to work with, especially in Godot. There's in 3D, I know for a fact that navigation meshes have a problem with being updated. That's why I want to focus on heuristics and like being able to create agents that move autonomously. Then over here we have boxes, which are just static bodies. It's the exact same thing in the tile map when we go over here and have a white tile like this. When we have a white tile like this, but when you have a collision shape, it's the exact same thing as setting up a static body. Then over here we have like 3 enemies. So let's start off with the player because I think that's the most simple scene we have. And over here with the player, we have the kinematic body 2D followed by a sprite and collision shape. And in the script for the player, we have it's very simple. We have a physics process function which is making a velocity variable. That velocity variable is going to be comprised of a function called getVelocity and speed. Over here we have the code that lets us get our input actions. As you can see over here, if we go to project settings, input map, I scroll down to see UI down, UI up, UI right, and UI left. You just have to make sure you set it up with a key and then like click A for left, etc. As you can see, I've done that over here. And what we can do is, this is slightly complex, but what we could do is we could just make a a vector called v. It doesn't matter what you call it, and then v dot x. So on the x component, we'll be moving left or right. So input dot get action strength gets us a value between 0 and 1. So if I'm clicking the right arrow key, it will be 1 minus 0, right? Which will move us to the right. And if I press the left arrow key, it will be 0 minus 1. I think that's pretty self-explanatory. I'm pretty sure I have other videos that explain that topic as well. And we're just going to set v dot y, so our up and down direction. So being able to move up and down like this is handled by the y. And as you can see over here, it's very simple. I just want to speed through this to get to the enemy part. So when we're looking at the enemy itself, at the enemy scene, we can see it's a bit complex. But before we talk about that, I want to explain what we're trying to do when I say heuristics and autonomous agents. What am I trying to say? So let's say the red squares are enemies and this green circle is us, okay, or you. In a game, in a video game at least, what the ideal situation would be is that the enemy would be able to find you, right? Either by going around, like this, and they'll try attacking you, or if it's if it's a ranged enemy, at least it will try to go to a point where it can no longer see you. This tutorial focuses on enemies like this, where they try to go around and try to physically melee the player, try to attack the player, but I'm pretty sure the logic and the explanations I give in this video can easily be extended to an enemy trying to like move into the line of sight of the player. So if this red enemy was able to move over here, because right now it's being blocked by this white box, it would be able to move into a direction so that it could see the player and then fire its projectiles to kill the player. But that's besides the point. What we're trying to figure out is how can we make sure that these red squares are able to figure out, oh, I have to go around, or instead of around, like not go this way or not that way. How can I go towards the player? Well, we just I just said what we have to do. We have to try going towards the player. But that's kind of a difficult question to answer sometimes, because if we were trying to go towards the player, it would make sense to go this way. But that a human, like a conscious organism, would be able to say, "Hey, that's not the correct way to go. You would want to go around in some way or some fashion." How can we program that in? Well, we could ask the agent or the enemy to check before it went in a direction. Hey, are these directions valid? Like this with raycasts, and because that's a thing in Godot, and we can ask it, hey, if this direction isn't valid, don't go that way. Okay, if that direction isn't valid, let's get the next closest direction that's possible. So it would be these two, and then either like based on random or just based on the position in the scene tree, we could choose one or the other. And this raycast logic even applies over here. Let's say we had raycasts coming out of this. Whoa, we have raycasts coming out of this agent, and you notice that I'm not drawing the same amount of raycast, and I'll show examples of different amounts of raycast and what I think is a good number, which I obviously found through experimentation, but I implore you to do your own experimentation. But as you can see over here, we have this other agent with more raycast, but it doesn't have to check anything. We already know that this is the closest direction, or yeah, this is the closest direction, and we're going to be heading in that direction. So sometimes we don't have to check, and we could just move in the direction closest to the player, which is simple. But let's say for this last example, we have raycast coming out of this enemy, and as you can see over here, this we have a small issue. This and this are technically closest to the player. Um, if I draw in a green arrow over here, this and this are technically almost, let's just say, through approximation, that they're the same distance. How do we know which way to go? The thing is, there's a couple ways you can handle this, and I'm just making a simple tutorial to get the basics out to the public. But what you could do is you could have more raycasts. Like for example, you could have a secondary raycast right behind it that checks ahead and further. You could have, or you could just leave it up to random chance, which makes your AI a bit more dumb and easier to kill. But at the same time, you don't want to make something like, you don't want to make every enemy the Marauder in Doom Eternal, or like a boss fight. You want to make sure that there are some dumb enemies as well, which is part of game design. So you can see over here that we can't really decide between these two directions. So the solution is either we can extend and make our systems more complex, which is usually the answer in many situations, by having extra we can have extra raycasts which check like a step in advance, or we could just extend the Blu-ray cast themselves, which both options work perfectly fine. We could explore that later on, but for the sake of simplicity, for a quick tutorial, we're just going to say we'll just leave it up to random chance. Okay, so in this walking towards enemy scene, we have our kinematic body 2D. Usually you would want to make your enemies kinematic body 2D. You should not make them areas. You should not make them rigid bodies, or I should actually explain. You should not make your enemies areas or area 2D. You should not make them rigid body. Please do not do that unless you want your enemies to be unless you want your enemies to be some sort of bouncy ball. Please do not do that. Please leave your agents or player enemies as kinematic body 2Ds if you want to control the physics of it. Please do that. It took me a long time to learn that, and I'm telling you right now. Leave it as kinematic body 2D. Over here we have a sprite, collision shape, basic stuff. We have a position node, which actually house all of these positions. I'll get into that in a second. And we have our ray node over here, which is actually the raycast, which are the exact same blue over here that help us detect in advance. And when I'm talking about this yellow raycast over here, that is extending a little bit further. That would just be making a new ray node essentially, and then in each one of these you'd have to just extend it a little bit further, and then also check in advance. And then we have a random clock, whatever you want to call it, which we will talk about when we get to the code, and we have a body checker, which I will get back to at the end of the video. But why do we have to position them in such a specific way? If I just move this ray node over here, and then I just grab the position node and I move it over to the side, why do we have to position these in such a delicate way? Well, if you think about it, what we're trying to almost do is build a self-driving car, if you think about it, with a very particular goal, with a very particular goal in mind. Um, because what you have when you have a self-driving car is essentially a agent, right? Let's say it's a red rectangle, or like our enemies over here. Let's say let's just say the self-driving car is kind of like this. What the self-driving car is trying to do is it's trying to check around it. At least I know this is true for Tesla. At least that they actually try checking around the car what's there. Of course, they have refined sensors and algorithms that let them know what it's seeing, but we don't care about we don't have to care about what it's seeing in a game, depending on your game at least. And in this simple example, we don't have to care about what we're seeing because what we're seeing is wall. We don't want to go towards the wall because that's a dumb thing to go towards. We want to go towards not wall. And what is not wall? Not wall is, or something that is not a wall is going to be the player. And we could do that by checking the distance closest to the player. So we could literally take these points, or actually it would be better if we went over here and we can check the points where the raycasts are, and we can just check the distance towards the player. Now I'm saying points. Raycasts don't play well with points from my experience. Um, you could use them. You could use the global position of your raycast, but I would just prefer it if I had a position. I would just prefer if I had a position 2D that was these points, and then I would compare the distance squared from here to here, here to here, here to here, etc. And then I would compare those distances and see which one is the closest. And I would also check at the same time if a raycast is colliding. It's a simple logic statement of uh, is the distance between player and me the shortest? If yeah, it is. If it is the shortest, then and if yeah, it is the shortest, and the raycast in that direction is not colliding with anything, is not colliding with anything, then move in that direction. Move in that direction. So it's simple to think about these things, but when you try to put them in practice, it might go wrong, and this is where the tutorial comes. As you can see over here, we have our positions, and these positions are the exact same thing over here. I just wanted to remind you of that. And when we place these, and by the way, I did hand place these, and you do have to hand place some of it, because if you think about it, in the self-driving car, these sensors are hand placed for a reason in certain direction. It wouldn't make sense to just have them all on one side. That's dumb. We have to kind of space them out evenly by hand placing them. And over here with our ray node, we could just place it back on top. And yes, you have to go in and you actually have to set the raycast to like 30, like Y30. You cannot rotate it. Please do not rotate the raycast. It will not work properly. You have to actually set it to casting in a certain direction, and then it works. And you have to do that for each one of these. And I'm just going to show the values that I thought work fine. You don't have to do these values. You could have much longer raycasts, you could have shorter raycasts, whatever you want, but I found 30 works okay for this demo. And we could just place the ray node back over the walking towards enemy, and then we could get into coding it. In our walking towards enemy script, you can see over here we have declarations to a couple variables, which are position nodes, and ray nodes, which are all the positions that we'll be checking. We'll be looping over all of these positions over here. We'll be checking this one with reference to the player, this one with reference to the player, this one with reference to the player, etc. And we'll just be like looping over them and trying to see which one is closest to the player. Hopefully that makes sense. And speaking of the player and moving towards the player, we would also have to declare variables about that. So we have our velocity variable over here, which will tell us how to move, which direction to move, and we have a player variable, which is a declaration to the player itself, and we could check where the player is. So, for example, it would reference to this. Let's say this is now an enemy. Our car has turned into an enemy. We get reference to the player, and then we want to check each of these distances on position nodes. With reference to each position node, we want to check how close is it to a player. And if you give me a second, just placing the player in real quick. Let's say the player is over there. We're just going to be checking the distance between here to here. Actually, technically, it should be the center. So over here to here, here to here, here to here. And I could keep going, but you get the idea. In fact, I'm going to keep going. We're just going to be checking the distance from here to here. And as you can see, after we compare all these distances, we figure out that the one that's the closest is this one. But if there's a white thing in the way, or like a wall or a block, then this one will not be valid. We'd have to go this way or this way, because those are the next closest one, which is a good concept to think about. The next best option. So this is a really bad way to get a declaration to a player, but it's also a very good way to do it if you're doing a rough sketch or a rough prototype or demo of something. As you can see over here, we have our enemy over here, and we have our player. This code, this line of code will not work if you have your enemy underneath another node, because if we read it line word for word, get parent. Okay, we're going to ask our enemy over here, enemy, can you please get your parent, which is up here. Okay, so enemy gets its parent, and then it looks inside of this node. Hey, is there anything called player over here in any of these four? Which is one of my children. Is there a player here? No, it's not. And then your game's gonna crash. But if your enemy is like over here on the same level as the player, it's this enemy is going to ask, okay, get my parent. Okay, world, do you see anything called player? Yeah, I see something called player. Here you go, and it will give us a reference to that player. Okay, done. Random talk. So if we go back to our enemy scene, we have this random talk. It's just a timer. Dot connect. We're just connecting a signal to timeout to self. We're connecting the timeout signal to our enemy, and we're going to call this function random tick. Get it? Random talk, random tick, whatever. Every time the timer times out, and then we have a body checker, which is just a area 2D, and it's going to help us check if we collide with a wall, which I said I'll get back to at the end of it. I guess we could just discuss those two functions about random tick and body collide. So essentially what we want to do is we want to make sure, okay, I really didn't discuss the idea of the concept of time, but I guess I could go back and explain it. If we think about our self-driving car, for example, if we think about it with reference to it moving, as the self-driving car moves on the street, it's like checking its environment every millisecond. It's double checking, hey, did I get closer to this? Oh, yeah, if I did get close to this, okay, let me react in a certain way. Our agents over here, these red rectangles, are not that intelligent. They're not going to be checking every millisecond. We could tell them to check every second, though. That's perfectly fine, and that's exactly what we could do. So we could tell it to check like every we could tell it to check every 0.01 to 0.5 seconds, which is basically milliseconds, but whatever. And that's kind of what we could do to make sure these guys are moving quickly. In my experience, 0.01 doesn't work. What you have to do is kind of like 0.5-ish or 0.1. And in fact, you don't even have to do it. Sorry. You could basically do something like this. But in my humble experience, I found that timers don't work well for like 0.01 wait times. You want to do it in the physics process function, or yeah, the physics process function, which is every frame, and we could actually do that in a second. But we'd have to declare this move towards player function. This move towards player function is very simple. It's I'm going to show you the code right now. So we're just going to set our velocity variable to velocity to move. What's velocity to move? Well, we're going to get a vector to move towards the player. We're going to normalize it, and then we're going to multiply by 300. If we go back over here, if we think about it, what were we trying to say when we asked the question, which direction do we move? Well, we were basically asking, get vector to move towards player. That's a question we could ask the computer, and the computer can say, okay, I'm just going to do this orange statement over here. If the distance between the player and me is the shortest, then I'm going to move in that direction. Given that there's nothing colliding with me, then I'm going to give you a direction that I think is the best idea. So that's exactly what get vector to move towards player is. If you're wondering why the hell this works, well, when I define the function, it'll make sense. And just before I go on to explain this, as you can see over here, the get vector to move towards player returns a vector too. So that's why we could do something like this. This is the idea of returning a value from a function. If you're not familiar with that, I have no clue why you've made it this far in the video, but whatever. And over here we have our physics process function, which is just telling us to move and slide by velocity. You don't really need this part, but it works better if you have it. Okay, how are we going to check and actually move and like check the distances between players and points? How are we going to do that? Okay, this is the part of the video that you probably want to see. We're going to define a vector and a maximum distance. Remember how we're comparing the points, or like remember how we're comparing points around our enemy, and we're going to compare it to where the player is? Well, that's exactly what we're going to do. Well, how could we compare? What are we comparing against? We're comparing against infinity. If I control click it, infinity is a positive floating point infinity that is just the largest number ever, and we're going to be comparing it to these various points. And you're going to say, well, that's dumb. Well, the first one let's say this is the first one. The first comparison we make is obviously going to be yeah, this is the closest point. Well, yeah, exactly. But as we continue and loop over all the other points, we're going to find that it's actually not the closest. And let's say we're going in this direction, this counterclockwise direction, and we reach this point. Well, we can say, yeah, this is pretty much the closest. Let's say for the sake of argument that it is. And then we try comparing it to this one. We can say, oh, well, wait, that's not smaller than this length. Let's ignore this. Ew, this is a bad one. Because remember, we started over here and we're going around. Then we can check this one and we can ask, okay, how far are you from this? Oh, wait, you're longer than this one over here. This means we can disregard you as well, and then we can just use this direction or this position, or we can continue on with this value. And we could actually represent that idea by another variable called position to use, which will become apparent in just a second. So what we could do is we could actually just tell Godot for node in position nodes dot get children. So we're just going to be getting access to every single position over here. We're going to loop through them, and we're going to say the distance between them. Okay, first we're checking the distance. Remember, according to this orange statement, if I just go to paint, is the distance between player and me the shortest? Is the distance between player and me the shortest? That's what we're checking first. Why are we not checking raycast first? Because raycast can be expensive, and we don't want to check something if it's not the shortest. Imagine if there was a white wall over here, and imagine if we checked, okay, are you colliding? If you're colliding, okay, let's ignore you. And then now let's check your distance. That doesn't make sense, because why would we check why would we check if you're colliding if we don't even know if you're a point worth going to? So that's why we have to check our distance first. And the reason I'm using distance squared is because the square root operation is actually very heavy on computers to some extent. Don't blame me. There we go. I'm not dumb. I knew it. This YouTube video explains the fast inverse square root, and and it's a really good, interesting video about math and how you could avoid using the square root, because it's a very slow function in this video, as this person explains. Why am I not subscribed? But essentially, if you watch this video, which I will leave a link to in the description, this video explains like why square roots are kind of difficult to compute and whatever. I'm not trying to show it. I'm not trying to show their video, but you get the idea. Square roots not the best. If you avoid square roots are not the best. Try to avoid them if you can, and that's why we're using distance squared too. So continuing on, if we have our point over here and we're just looping over it, let's say we're starting over here. To continue the example from last time, we're starting over here. We're going to be, if we're starting over here, we're just going to be working with a node. So for example, we're starting with this one over here. We're starting with this one over here. Same idea. And we're going to be checking its distance, and we're going to check the next one. And each time we do that, we are going to be comparing it to the maximum distance, because that's what we want to do. We want to find the shortest point towards the player. We could do if distance is less than maximum distance, and right away we could say, if that's true, then set the maximum distance so far equal to distance, because we want to make sure we get to the minimum value. So we can do that. We want to make sure we get to the minimum value, then cut after that. After we check if it's a point worth going to, remember I said point worth going to before, we can then check if this raycast, and by the way, you don't have to do this. You could just leave it like this. That's totally up to you, but I prefer static typing. And because we know in the ray nodes, .getChild will always return a raycast, we can just kind of assume that we'll always have a raycast 2D or raycast regular. If you're going for a 3D game, but whatever. If you're wondering where this I is coming from, it's coming from over here. How are we going to increment it? Well, after each node, we can just increment I plus equals 1. That's not that hard, but you have to make sure that if you have 8 or 9 points, you have to have 8 or 9 rays. You have to make sure those values are consistent, or else you're going to get a crash. And it's not like it's a game-breaking bug, but you'll definitely catch it before you launch your game. It's not that hard to pick up, even if you miss. It's actually a better idea to put this max distance equal to distance over here, because if you think about it, we want to make sure that this point that we're going to is actually a point we can go to. There's a slight subtle difference in the language I use. The point that we're going to, which we're checking over here, and we want to make sure that it's a point that's valid. So, for example, if we're checking something over here, we check, yes, this is a good point. We check this one is closer, but we want to make sure that it's, first of all, valid, that we're not colliding into a wall, and then we want to set the max distance. Because if you think about it, if we left this line up here, then we would be stuck forever moving in this direction, and we have a dumb AI. A dumb AI that just moves towards the closest point that the player is. We want to make sure that it's checking its surroundings. Hey, is this a point I can go to? And you might notice this line over here, which is position to use equals node.global position. We want to make sure we have this because we want to make sure we get a reference to what is the direction we will be heading toward. Otherwise, what's the point of doing this calculation? And speaking of direction, we could just easily do something like this, where we say if this position to use is a valid thing and we found one, then we could just set the vector equal to position to use minus global position, which literally just says, oh, look at your self-driving car or enemy or agent, and then subtract the distance from here to here. And that's essentially just a direction, a vector pointing in the direction we want to move. It could be for any direction, doesn't matter. And then we will return vector, and that closes this function up. A very long, convoluted way of explaining move towards the player if that direction is valid. And we can see over here, we return that vector, whatever that vector is, whichever direction it is. As long as it's not colliding into something, that's a no-go. We're not going to return that, but we're going to return like going around stuff. And then normalize it because it's technically not normalized on the diagonals over here. It will return something a bit longer. So that's something you might want to keep in mind, and multiply by a speed variable. If you want, you could do var speed equals something. Sure, go ahead. Doesn't matter. But yeah, I shouldn't have hard-coded that in. And then velocity is equal to velocity to move. And you can see over here, that velocity that we're talking about is actually going to be used in the physics process function. I remember saying when I was recording, we could do it over here as well. And if we run the scene, we have an error. Why do we have an error? Because if you think about it, we have the player right now in the scene. That's not a good thing. And we have another error. Hello? Oh, okay. The error over here is because I forgot to rename those. And you can see over here that we're basically moving towards the player. As you can see, they're able to, we're able to go around objects. Like, okay, these guys are stuck, and I'll explain how you could fix that. But you can see that these guys are able to go around simple objects. But as you can see, we generally have a system where these agents can pathfind towards us, although they might get stuck sometimes. And this is just a simple tutorial, like explaining the first iteration of it. We will extend it more and more as we continue, as I continue this series. But you can see that they're able to overcome basic obstacles and find us, technically. So how could we improve it, or ideas for extensions? Well, instead of doing every physics process function calculate, we could do it on a timer. So over here for the random tick, we could actually move towards player then. It makes it a little bit more of like a pink. It makes the AI behave more like a Pinky from Doom or Doom Eternal or whatever Doom game you want to talk about, where it charges towards you in a straight line that makes a beeline for the player. You can see what that looks like, and essentially you can see that they're a lot more robotic, but they're also less likely to get stuck because, as you can see over here, they're able to overcome that. These two are getting stuck, and one way you could use, a really simple way you could fix that is with going by this and going over here and actually modifying the activation function, or the function that lets us choose if a point is worth going to. So you could do something like random float less than some random value, like let's say half. Oh, okay, that actually makes sense because it wasn't ever going to find a point to move to it. And if we implement this random function over here, just randomly not going towards the player or not moving towards the closest point where the player is, you can see that they do become a bit dumber, and it's a little bit harder for you to predict. So it would, and this kind of relates to the language I used at the beginning of the video where I said agent. Now these aren't really enemies anymore. They're kind of like wandering mobs, or just mobs that generally happen to move towards the player, which might make for some interesting interactions in your game. Who knows? But of course, this is just a simple basic tutorial on basic problem solving with trying to figure out how to move towards the player, trying to move a non-player character towards a certain target that happens to be moving without navigation meshes. That's all I really have to say for this tutorial. Thank you so much for watching, and have an amazing day. Whoops, I forgot. Yes, this AI is dumb. As you can see over here, right now, I am exposing myself and saying this AI is not perfect. It's garbage. It's kind of trash. But I'm hoping I can get people to understand the basics and use this video as a jumping point towards making their own AI. For example, I could easily have gone further in this video and explained a system for not moving in the direction that you just collided with. That's not that hard, but I've already been recording for quite a long time, and I don't want to make this video any longer. So that will be coming in another part in the future. But right now, let's start off with getting something moving and not colliding with walls a good majority of the time. As you can see over here, it is kind of doing what we ask it to do, but it could be improved upon. As you can see, it does get stuck. I'm not trying to say this is flawless, but this is a jumping point towards understanding systems like that. It's systems that you see in professional video games, like let's say Doom Eternal, which is the best example I could give, with really good AI. That's a point toward, like, getting towards a point where we could make something like that. Yeah, that's now I'm done my rant. Okay, have a good day. Holy shit, it's been 5 minutes. Wow, how long has it been? Oh god. Okay, wow, I can't believe I finally was able to explain that concept after 20 minutes of rambling. Okay, so after that, a better way would be to use singletons and autoloads, which is actually a very good tutorial idea, and I'm going to write that down right now.